Okay, this is going to be the lecture video for chapter 12, all about gravity. So we're going to talk about Newton's law of universal gravitation, gravitational attraction of spherical bodies, Kepler's law of orbital motion, gravitational potential energy, how it relates overall to energy conservation, and then I'm not going to go over tides because it's not really tested, but they are in the slides if you want to read more about them. Okay, so in addition to figuring out the acceleration of gravity, Newton also came up with a law of universal gravitation. So his thought was, hey, there's this force that accelerates an apple downward. It's got to be the same force that keeps the moon in its orbit. So he just went beyond. So his equation that he came up with is the force of gravity, right? So you can rewrite this as Fg if you want, is equal to big G, which is a constant. Okay, this is called the universal gravitation constant, and it's 6.67 times 10 to the negative 11. Okay, this number is super, super small, but you multiply it by the mass of the two objects in question and the r squared, which is the distance between the two centers of your object. So for this law, you always measure from center to center. So the gravitational force is always attractive, and it points along the line that connects the two masses. So if mass 1 was the Earth and mass 2 is the moon, their force of gravity between them is going to be attracted to each other, and they're going to be equal to each other because of Newton's third law of motion, right? So these two forces are an action-reaction pair. And then the r is the distance between the center of both objects. R is measured in meters, mass is still in kilograms. That hasn't changed. So the gravitational constant is a super small number. That means the force of gravity is negligible unless there is a very large mass, such as the Earth. Then it becomes more relevant. So you can calculate the force of gravity between you and a person next to you, but it's probably going to be super, super small because your masses are not as big, you know, like the Earth or anything, to really make a significant change. So if an object is being acted upon by more gravitational forces than just one other one, then the net force on it is the vector sum. So just like you took the vector sum of your forces acting on one object, it's the same principle for force of gravity. There could be multiple planets and moons around, like Jupiter, right? So then you just take the vector sum of all of those force of gravities. We call this the principle of superposition. So most common examples for force of gravity calculations are between two spherical objects, like two planets, two moons, the sun and the moon, the sun and the Earth. The force is going to be the same to each other, and for our point of reference, we assume that the mass is concentrated at the center. So we measure the r from center to center. We assume all the mass is concentrated at the center. It just makes our calculations a little easier. So if we take into consideration the gravitational force for objects that are at the surface of the Earth, right? So if you want to calculate the force of gravity between you and the Earth, because we are on the surface, then for the distance, you just use the radius of the Earth. So you can rewrite that force of gravity equation to be the mass of the object on the surface times the mass of the Earth. That's what this E refers to, is the Earth. divided by the radius of the Earth squared. So you can rewrite it this way if you want. It really doesn't matter, whatever is easier for you. But all in all, what you can say is that this force of gravity equation, right, that you just learned, is the same as the mass of one object times the acceleration of gravity. They are the same. They are equal to each other. So going back to little g, which is acceleration of gravity, that negative 9.8, it is not the same everywhere on Earth. Specifically, if you have super high altitudes, then it's actually going to decrease a little bit. It's not going to be a super significant difference, but you can see the overall trend of the line of the acceleration is going to decrease just a bit the higher and higher you go. When it gets to a certain height, then it becomes more significant. So usually when it leaves the Earth's atmosphere is when acceleration of gravity really decreases. And you can see that on this chart here. So acceleration of gravity, closer to the 10, gets super, super high up, it's going to decrease exponentially. So measuring that gravitational constant also gave us a way to calculate the mass of the Earth. So rearranging your equation to solve for mass of the Earth, you would get this. All right, Kepler's laws of motion, or orbital motion more specifically. So Kepler made all these studies of planets and their motions over many years, and he was able to make 3 laws as well. So the first law of his says that planets will follow elliptical orbits, aka like an oval, with the sun at one focus of the ellipse. So if you don't remember, an ellipse, you have 2 focus points. So the sun is at one of those focus points. His second law of orbital motion says as a planet is moving in its orbit, it sweeps out at an equal amount of area in an equal amount of time. So depending on where it's at in its orbit, whether it's closer or further away from the sun, it still covers the same area in the same amount of time. His third law of orbital motion says that the period of the planet is going to increase as the average distance from the sun is raised to the 3/2 power. So it can also be shown as an inverse square form of the gravitational force. He did many, many studies, and this is what formula he came up with. So like Newton has his 3 laws, and one of them is formula-based. This is Kepler's version of that. He has his own law that's formula-based. So you have different types of satellites. A geosynchronous satellite is one who has an orbital period that's roughly equal to 1 day. So if you have a satellite orbiting above the equator, for example, it's going to be in a fixed position with respect to the ground, and it goes around and orbits in a day just like the Earth does. So these kind of satellites we can use for communications and weather forecasting. GPS satellites, however, are not in geosynchronous orbits. Their orbits is 12 hours, so about half a day. And they use triangulation of different signals from different satellites around to allow precise location of objects on the Earth. So it's not just one satellite that does GPS, it uses multiple, and gets a more accurate reading. And his laws gave us more insight to possible orbital maneuvers. All right, so we know that orbits are typically in ellipses. So based on what kind of objects are being out there, like if we throw a rocket out there, then their thrust can have an impact on their orbits, and they have what's called an elliptical transfer orbit that can help them go out to the regular orbit that it should follow. So he did all this math and gave us kind of like little pathways they can go to. So going back to gravitational potential energy from the energy unit, we knew that gravitational potential energy is equal to mass times gravity times the height. Well, using that gravitational constant, you can also say that the gravitational potential energy is equal to negative gravitation constant times the mass of the object times the mass of the Earth over the distance. Right? It's another way to calculate it. So if we are super close to the Earth's surface, then we're going to use our MGH equation because it increases linearly with altitude. We know energy is a scalar. There's no components, it's just a sign. So if you want to calculate the total mechanical energy of an object from a distance r from the center of the Earth, you know that total energy, total mechanical energy, is equal to kinetic energy plus potential energy. So there's your kinetic energy formula again, but then this time we would use the gravitational potential energy using that constant. So this also confirms that as an object approaches Earth, it's going to move faster and faster. This helps prove that point. So here's a graph showing you. So the further away your object is from the Earth, like way down here, your gravitational potential energy is not going to be as big, but as you get closer and closer to the Earth, it's going to level off and then create that linear slope that we know as MGH. You can also calculate the escape speed of different objects, different projectiles that they need to escape from the Earth's gravity. So you can do this for any planet if you have the right data. So square root of 2 times gravitational constant times mass of the Earth divided by the radius of the Earth. So when you plug all those values in, it's roughly 11,200 meters per second or 25,000 miles per hour in units that we are more used to. But like I said, if you have the right data, you know G and the mass and the radius of other planets, you can calculate their escape speed. So here's a graph of different speeds of a projectile as it leaves the Earth for various launch speeds. So when an object is launched from Earth, right, it's not going to go at the same speed, but you can see that the closer it is, the less escape velocity, further it is, it's going to increase.